Hey, geometry students, in this lesson we're going to be talking about cross sections of solids, and I think this is a fairly straightforward lesson. Honestly, it's a little bit difficult to teach this lesson because there's not a whole lot to be said about cross sections of solids. You kind of just have to figure it out. Okay, so a cross section is the intersection of a three-dimensional figure and a plane. And our book says to think of a cross section as the shape that would be revealed if you cut straight through an object along that plane. Now, there's some pointers and some tips that I can give you in identifying the shapes of cross sections, but a lot of this is just really deeply thinking through what the shape would be. And if you can't figure it out by thinking it through, just really carefully looking at the figure to see the shape that's made where the cross section intersects the or where the plane intersects the three-dimensional figure to make a cross section, right? So that's what we're going to be doing. You're going to find that the answer to these questions mostly pretty straightforward. Sometimes we're going to be asked for shapes. Sometimes we're going to be asked for perimeters or areas. Okay, we just have to infer from what we're looking at what the perimeter area measurements are. So let's take a look at our first problem. If the plane is parallel to the prism's bases, what is the shape of the cross section? I'm going to say this. One rule of thumb that you can follow when considering cross sections is if that a plane is parallel to a figure's bases, the cross section is probably going to be the same shape as the base. If it's a prism like this, it's going to be the exact same shape and size. We're going to see in the next one, if it's a pyramid, it's going to be a smaller sized version of the shape of the base. So what would the shape of the base be here? The cross section is probably just going to be let's see, this is a hexagon, so it's probably just going to be a hexagon, right? Let's take a look. The cross section is a hexagon. All right, letter B. Find the perimeter of the cross section of the square pyramid. If the cross section is parallel to the base, so it's going to be the same shape as the base. What is the shape of the base of the pyramid? It's a square. But now, it's not going to be the same size as the base because the square gets smaller and smaller as you go up toward the top. One side of the cross section is 4 inches long. Okay, so the perimeter of a square with one side 4 inches long is going to be 16 inches. Let's see if that's right. There we go. Letter C. Find the perimeter of the cross section of the square pyramid. Okay, now look at this cross section. This is a different one. We are cutting perpendicular to the base. And oftentimes when we cut perpendicular to the base, now most planes on figures like this that cut perpendicular to base are not going to be like the perfectly triangular shape that this one is. If I cut like way over here, I'm going to get a trapezoid instead of a triangle, right? But if I go right through the vertex of a pyramid, my cross section is going to be a triangle. And this is one of those where it's hard for me to give you a rule of thumb that works in all cases, but you really just have to think through what would the shape be if I cut a pyramid in half at its vertex. And you can consider that it has to be a triangle. All right, so let's see. The height of the pyramid is 14 inches, and the base of the pyramid is 12 inches on each side. Okay, so let's think about that for a second. I don't know that the height of the pyramid matters, but if the base is 12 inches on each side, that means that the base of, oh, it does matter. The height does matter. The base of the triangle is 12. Okay, so let me do this. Let me just draw the cross-section triangle. We're going to say that this is our cross-section triangle. It's not necessarily an equilateral triangle, okay? So I'm gonna just make it a little pointier than maybe it has to be. And what we know is the base of this is 12 inches. Can we figure out what the height of this thing is? Well, we can, because I know that half of the base is 6 inches. So I'm just going to cut that in half. And then I'm just going to drop a vertical down here. And what do we have? What do we have? We have two right triangles here. Do I know any other sides of my right triangle? Well, I know that the height of the pyramid is 14 inches. So I know that this height right here is 14. And now to find the perimeter of the cross section, I need to find this diagonal here. That's a Pythagorean theorem problem. This is a Pythagorean theorem. So let's just do this down here. And we're going to say that 14 squared plus 6 squared equals whatever the hypotenuse is squared. Oops, hold on. So it's going to equal the hypotenuse squared. I'm just going to call it c squared. Okay. So 14 squared plus 6 squared. I'm just going to use a calculator for this. And we're going to get 15.23. So I'm going to put 15.23 along both hypotenuses for this triangle and this triangle. And then to find the perimeter of the triangle, we need to add 15.23 plus 15.23. That's going to be a total of 30.46 plus the 12 at the bottom. 42.46. Let's just make sure that's correct. 42.46 inches around this triangle. Let's move on to our next cross-section problem, which is going to be the cross-section of this cube. Now, this is not a cross-section that's parallel to the bases. It's not a cross-section that's perpendicular to the sides and the bases. This is going to be a diagonal cross-section. So we have to think about what this is going to look like. Now, we're told in the problem that this is a 4-centimeter cube. Each edge is 4 centimeters long. So that means that at least I know that the sides of the cross-section on this side and on the far side have to be 4 centimeters. But the diagonal's not going to be 4 centimeters. It's going to be greater than 4 centimeters. So we have to think this one through. Now, here's what this is going to look like. If I consider this cross-section, again, this is just me thinking about what's going to happen when I slice the cube and look at its face. The new face that's formed by the cut is going to be a rectangle. And the edges are going to be 4 centimeters. But what is the width of this rectangle going to be? I'm going to need that to find the area. Well, let's think about this. If I'm looking down at the cube from the top, okay, so I'm looking at this triangle right here, but exactly from the top, it's going to look like what I've drawn here. It's going to have sides of 4 and 4, and the hypotenuse of this triangle is going to be the width of the rectangular cross section, right? Can you see that? That this hypotenuse here is going to be this length along which this cross section goes. So how do I find that? Well, I'm just going to use Pythagorean theorem. So when I look at this triangle, I realize it's just going to be 4 squared. Okay, so that's one of my sides. The other side is the same length, so it's going to be plus 4 squared equals c squared. And then I just need to figure out, oh, so 4 squared is 16, plus 4 squared is another 16. So it's going to be 32 equals c squared. So I just need to find the square root of 32. And to calculate the square root of 32, I'm just going to use a calculator. Square root of 32 is 5.66. So it means that this width on the bottom here, I'm just going to put it down here. Oops, let's just do it that way. Is going to be 5.66 centimeters, 5.66. Okay, same with the one on the top, but it doesn't really matter the one on the top because I just need one length and one width to calculate the area. So my area is going to be 4 times 5.66. So let's go ahead and calculate that. All I need to do is multiply this times 4, and that gives me 22.63. Let's check and see what the area was for this one. 22.63 centimeters squared. All right, for letter E, we need to consider another relationship. So Cavalieri's principle states that if two solids lying between parallel planes have, okay, so let's just pause there. Lying between parallel planes means that their bases are in the same plane and their highest point is also in the same plane, okay? Or if they have two bases, one base is in one plane, the other base is in another plane. But the planes have to be parallel. And they have equal heights, okay? So notice that this cone and this cone have equal heights. They lie between parallel planes. And all cross sections at equal distances from their bases have equal areas. So if I think about it, if I go halfway up this cone, there's going to be a circle that has a certain area that's half the area of the circle at the bottom of the cone. Well, if I look over here, this circle halfway up is going to have the exact same radius and it's going to have the exact same area. Okay. So as I go up the cone, if there's a corresponding circle in the other cone that has the exact same radius and the exact same area. If that's true, then the solids have equal volumes. Okay. And here's what that means. This is actually a really simple principle to apply. I can use my formula for the volume of a cone to work for this cone or for this cone. It doesn't matter if it's an oblique cone like this. The formula for volume is going to work the same as long as the heights are the same. Okay, so even though this is an oblique cone, I can still calculate the volume of this cone using the formula for the volume of a cone. It works for any cone. And the formula you might remember for the volume of a cone is 1/3 times pi times the radius squared times the height. 1/3 pi r squared h. Okay, now this looks like it's going to be pretty simple. Just plug in 2.5 for r squared and then 13 for h, right? Well, not exactly, because look at what the height is. The 13 is measuring along this oblique length here, but I don't need that length. I need h. And one other thing, it says to find the exact volume. So I'm going to find volume in terms of pi for this one. So this is going to be a little bit more difficult than it looks initially. So here's the first thing I need to do. I need to consider that this cone is a lot like a right triangle. If I were to take a cross-sectional, oh, look, I'm doing a cross-sectional area. If I take a cross section of the cone here, it's if I cut it straight down the middle, it's a right triangle, and that helps me calculate what the height is. Okay, so let's consider the right triangle at the cross section of this cone. It's going to look like this, and then let's see, the length of the base of this right triangle is going to be 2 times 2.5. So 2 times 2.5 is 5. That's going to be 5 centimeters along the base. Okay. And then the height, I don't know what the height is, but I know the hypotenuse has to be 13 centimeters. Now, can I find the height if I know I have a hypotenuse of 13 and a base of 5? Well, the way that this is going to go is it's going to be a squared plus 25 equals 169. So I'm going to have to do 169 minus 25 equals this side squared. 169 minus 25 is 144. And so 144 equals the third side squared, or the height squared. When I take the square root of that, I get 12. So this is a 12 centimeter high cone. Now, I'm asked to find the volume. I'm going to plug in 12 for the height. We're going to leave pi as pi, and then r squared. Well, let's see. The radius is 2/5. Since we're doing this exact, let's do this exact, okay? So it's going to be volume equals 1/3 times pi times, okay, so the radius is 2.5, which is the same as 5/2, but it's going to be 5/2 squared because it's pi r squared. So 5/2 squared, that's going to be 5 squared over 2 squared, which is going to be 25/4. Okay, so I'm just going to note that. And then times the height, which is 12. Now let's see if I can simplify this at all. I'm going to cancel this 4 with a 4 from this 12 and make this a 3. 1/3 times 3 is just 1. So the answer to this one should be, in exact terms, 25 times pi. There we are, 25 pi centimeters cubed. All right, and that's how you work these sorts of problems. You just have to use your ability to envision what it would be like if you cut these solids along the plane to figure out what their cross-sectional shape is going to be, and then to do any calculations related to that cross-sectional shape. You ready to work the problem set for next time?